Hello everyone, welcome to my next tutorial, Degradations process of OLED. It is a newly added tutorial in the SetFox 6.0 version, therefore we are going to directly explain about this tutorials. And it is a 8.6 tutorials that I want to tell you, and we are going to explain about this tutorials and the SetFox 6 that's added new module as well as thermal modules. So before we start off this tutorial, I want to introduce myself again. I'm Sahil Verma, application engineer is the well-known company Impulse Technology. We are going to simulate in here the degradations process in OLED. As the degradations mechanism can be simulated, which allow to the access the impact of the different quenching mechanism on the device lifetime and analyze how charge and excitant profiles are modified during operations. So these are the separate tabs given in the SetFox: quenching, proton quenching, and lifetime. So you can use this tab to simulate this type of process. OLED degradation simulations using model like drift diffusions, kinetic Monte Carlo to predict the how display age. So these are the separate modules and these are the separate tabs. These simulations often performed with the softwares like SetFox. So we are here for the discuss about the SetFox software. So therefore we have attached this term. Physical process over time to calculate change the luminance, voltage, efficiency, allow researchers to estimate lifetime and sensitivity to design choices. So now I'm going to explain about the SetFox softwares. We have also the Lighthouse and Lighthouse lights that work for the LED stability. You can also use this type of softwares and you can visit on the Fluxim Ag website. Who has not seen it my previous video, they can visit. We have explained each and everything about the Fluxim Ag, their softwares, and about my company Impulse Technology, and number of the tutorials are given. So now I'm going to open the SetFox 6.0 versions and I'm going to explain how you can simulate degradations of OLED. Click on the right side and run as an administrator. It is a new GUI which is added in the SetFox 6.0 version. So you can see at the top side and that new versions that some of the things have given. So you can update if you want to do. They have already updated, so we can cut these points. It is the SetFox GUI for the SetFox 6.0. You can click on this for the new simulations files. If you want to see only that layer stack, so you can disable and you can see that layer names. In here you can provide the inputs, stack preview. These are the modules. About the SetFox 6.0 version, we have already told in the 4 terminal video. Who have not seen it, so they can check about this. Generally, OLED degradations, especially used for the blue device, it is a major challenge in a commercial applications. Intrinsic degradations mechanisms are commonly attributed to excitants and reactions. We have also examples for the OLED degradations.parse, but we are directly going to create one of the new simulations files. How you can create, we are directly taking from the layer names and thickness, and then I will provide the inputs. I hope you have already about that theory parts as well as too much. So therefore we are not covering too much theory. I'm directly showing the how you can simulate. Like you can add unlimited layer using these tabs and give one by one each of the layer names. Like first glass, then one of the conducting oxide ITO, whole transports layer HTL, one of the emissive layer you can take, ETL electron transport layer. You can add more layer stack because we need more layer. Aluminum and air. You can delete this layer from these tabs and you can see their name have created, but we need to provide in here the thickness as well as one by one. So you can provide thickness as well as in here ITO 25. Whole transport layer, it totally depend on your projects. According to your value you can provide and you can create same this type of structure. I'm taking one of the examples. emissive layer you can take 20 nms. Each parameter have the different meaning. You can also visit on the help tabs. You can see, and that input you have provided according to the your results will come. So you can use wisely your value. Aluminium 150 nm. Air you can give in the 100 nm. So you can see that layer stacks and thickness have given in here, and according to that your stack return you can check your preview. Now one by one we will be provide that refractive constants value. If you think that which is the wavelength dependent file, so you can give in here that .nk file formats. Number of the refractive index file formats are given, and material database as well as attended in here. When you click on this tab, you can see number of the material related to the wavelength they have given. So it is new tab that have added. Once again I want to inform these tabs. And refractive constant for the glass you can give 1.5. For the ITO it is a wavelength dependent. You can give in here that ITO.nk files. You can see that have the too much big library. For the refractive index files that supported .nk, you can directly search ITO.nk. For the whole transports layer, you need to import one of the STL layers. So you can directly go with this import tabs. You can choose according to that your STL layers. I'm just considering the examples. Emissive layer, you can give in here that one of the emissive layers. You can import one of the emissive layer. Same one by one you can import lk.nk. Aluminium you can import like this. For the air it will be refractive constant 1 that we have taken. In this tutorial that generally means as the luminance losses and expected luminance decay or voltage rise over a time. So this type of things you can see, and that types are also given in here. So now you need to provide one by one electrical as well as emissive parameters as well as. So first I need to activate that drift vision modules like this, and consider ITU as a electrode. In between the electrode you need to consider semiconducting layers. In between the electrode you need to give in here the injection models, thermionic organics. Work functions you can give in here the 5.15 for the ITO. Same for the aluminum, you need to give in here the electrode, it is a thermionic organics, and 3.25 work functions for the aluminum. In between the ITO and aluminum you need to provide semiconducting layers, and one by one you need to import semiconducting files. You can enable semiconducting, and now you can provide that semiconducting layers. You can see number of the material files are available in here. So you can import one by one. Like in here the you need to import STL constant. So you can directly search STL constant.em. You can see that STL constants and their value automatically fill in here, that excitant, traps, mobile ions and recombinations parameters. If you want to give any new parameters in here, you can give that temperature dependent diffusion coefficients. Different type of mobility models are given as well. You can see my different video, and you can see non-radiative decay rates, generation efficiency and excitant proton quenchings. You can see that tabs are given for the quenching. Not only the single one, you need to add different excitants, and trap given, acceptor, donor, neutrals, and trap density, blue LUMO, homo LUMO. You can see that. And at the bottom side you can see that degradations models are given from electron holes. So you can see, if you don't want to add these traps you can disable this. Now you can import one of the electrical file, and we want to calculate these layer degradations properties, so you can import directly that files eml3 degradations degrade.em file. When you import these files, you can check one by one each of the data charge. You can see field dependent mobility given, gamma and density of states, energy levels, effective density, units you can check, excitance tabs you can see, radiative decay rates, non-radiative decay rates, generation efficiency, diffusion constants, and quenching parameters for holes. When you jump on the traps, you can see enable trapping parameters, and you can see trap types, donor types, trap density and their value, trap energy, Eva Blomo. You can see field dependence, and if they are that dependent, so you can choose. You can see enable transient trap generations and from excitant proton quenchings. So that is the mandatory for that calculation. So you can visit on this new tabs degradation models. It is anion and cation calculations. If you want to do, you can use it for the recombinations. You can check. Now you can import ETL layers. As for the ETL constant, you can import. Then you can check one by one these parameters. According to this parameter, energy level I have created in here, excitants, traps and mobile ions and recombinations. So we have imported this semiconducting properties. If you move on the electrothermal settings, and you can see mode steady state. About this type of tab we have already informed, so you can check my previous video. Steady state, transients, AC, and you can enable that transients, and then you can enable that value. That value you have given in this semiconductings, you need to enable in here one by one, like trapping, trap generations for the degradation model, excitant, temperature should be same, electrical source voltage you can take in here, that's current, and 10 milliampere per centimeter square. It is that external load. If you want to connect, you can use this electrical circuits. In the transient signal, if you move in this tabs, you can add one of that tabs from here, enable the transient electricals. Currents level you can give in here the 10, and second you can give in here the 2 volt. If you move on the transient solver, you can see that's a numerical tolerance value. You can edit in here that's 4. Sport transients, you can give another log time steps 1 microsecond. You can select in here the millisecond, and step per decade 50. Sport transients profiles 1 second, and step per decade you can take in here that's 10. If you move out that termination criteria, you can set in the number of iteration 1. That type of value you can provide in here. You can check any value or any parameter you want to add, you can give in here. You need to enable now emission modules, and emission layers take it as the emitter. For this emission layer, you can see the different type of files: wide, detail balance, Gaussians and Lorentz. Units you can see distributions, different type of distributions, delta, exponential, Gaussian, excitant. You need to import one of the emission layers, so directly go with this. You can see different type of photoluminescence spectrum files are given in here, that supported .pl files. You need to import this files, balq.pls. You can see that file have imported in here. Unit will be probability, as they have changed y-axis arranged according to the probability. Dipole orientation, isotropics, and delta distributions, excitant coupled, because we have enabled that drift fusion module, so you need to couple this. If you move on this emission setting, you can check that different modes are given: dissipations, power analysis, mode analysis. But we need to enable that spectrals. You can give in here that's wavelength range 390 to 700 and 1 nm. For the default optic setting, you can give in here the 485. emission angle will be 0. You can check that different type of tabs are given in below sides. If you want to give or any value in here, you can give. Like if you want to reduce this STL calculations, you can enable that discretization tab. It is only for that calculation because set first calculate each nm, so you can reduce this calculations part for per nms on these elements. For the initial layer, you can take in here that element 40. Like you can check, you have provided one by one each of the value. Now you can check on that script modes. If you want to change any parameters, you can edit from here directly. It is editables, value, thickness, and that file you have imported, elements, electrothermal current, temperature, trapping degradations, excitant, iterations. So that's value you have provided. In here you can check. You can edit in here that setting because we have the starting point in signal at t equal to 0. It is a starting point. Whole scripts are given in here. Now you can give in here your simulations file name, OLED degradation, and click on that run button. You can check one by one each of the results in here. Reflected color, intrinsics, numerics as the time step, absorptions, reflectance, and transmittance. Any other transient profiles you can check, band diagrams, charge density, currents, electrical field, excitant density, excitant rates. You can check like this as well as potentials, trap density of states, trap density rates, trap capture rates, trapping rates. You can check one by one results in here, current efficient transients, components. This result for the microsecond. If you change for the second, and then you can simulate your project, so different result will become according to this seconds. You can check one by one band diagram, charge density. Same you can check emission transients. You can see like this. You can zoom, you can like this. If you click on the show all trap density rates, if you show all, you can see like this. Current balance transients, scene transient, device current components, SRH and no SRH you can choose, and the recombinations. And I have to check one by one each of the results. Internal quantum efficiency, luminous transients, radiance transient, trap density, and trap density state rates. So now I'm going to end here my tutorials. If anyone have query related to this, please ask in the comment box, as well as my email are given in the descriptions and end of the video. And who has not seen it my previous video, please check out the playlist. Thank you very much.